Welcome to the second lecture video for the week. We're going to pick up our discussion about algorithms and our analysis of algorithms for how efficient they are by continuing to talk about computational complexity. So we just looked at an example of computing a sum of n numbers using two different methods, one of which ran in linear time or had order n computational complexity, and another one that was order 1 computational complexity, or ran in what we would call constant time. And that's what we saw in this plot: a constant time solution and a linear time solution. We're going to carry on with this kind of analysis with another example, and we're also going to consider what we can do to improve the computational complexity of some simple computer science problems. So one task that we often face is finding some element of a data structure. As we discussed in the data structures lecture, we often need to access data, and we in fact compared two different data structures, lists and dictionaries, where we could look up some values. With a list, we looked them up by position, and with a dictionary, we looked them up by key. And we also discussed that underlying these two data structures are two different methods for searching for data. So for the list, to search for a particular element, we start at the beginning and advance until we find that element. Whereas for a dictionary, we can compute a hash of the key, and that tells us directly where in memory to look for that value. We're going to consider this this problem again and contrast or further explore these methods as well as another method. So we could write a function for finding an element in a list, and that function would accept a list as a argument, as well as the value or element that we're trying to locate. And just as I described a moment ago, to find the element, we would iterate through the list element by element, and if the current element in our iteration matches the element we're looking for, then we return true because we found it. It's in the list. And if we reach the end of the list without finding it, then we know it's not in the list, so we would return false. So we can make a random list using the random module, and we'll just fill it with random integers. So we have a list here of random numbers between 0 and 50, and we've got 5 of them. Now, just as we did before, we can time how long it takes to run this function to find a particular value in our list. So we'll write a little function here called timefunc that accepts the function we would like to time or benchmark, as well as any arguments we want to pass to that function. We start our stopwatch. We run the function with its arguments, and then we return the elapsed time. So this function is just going to, again, like we saw before with our compute function up here for making these graphs, this is just going to measure how long it takes to run our search in for a particular element in the list. I'm not going to break apart what everything in this function does, but if you're interested in understanding this function better and you're struggling to understand it on your own, you're welcome to ask about it on the message board, and I will gladly help you out there during office hours. So we'll just again set the number of times that we want to run the function and average together our results, and then we'll measure how long it takes to search for elements in lists ranging in size from 10 to 100,000. So we'll have lists with as few as 10 elements and as many as 100,000, and we'll be taking steps of 10,000 between each data point. And then we'll make a plot of how the amount of time it takes to find the element in the list grows as a function of the size of the list itself. There we go. So, unsurprisingly, this function runs in linear time in the size of the input. So we again see a linear relationship. And we could have guessed that because we have in the function this for loop where we iterate over the list. So as the list gets longer and longer, I'm going to be taking an additional step for each element in the list on average. If I had, for some reason, if I had two for loops here, say I had two lists and I was looping over them together or something like that, we would run a loop over all of list 2 for each step through list 1. So if both of these are size n, then I'll be taking n steps for every step in an input of size n. So we would get n for each of these. So that'd be n times n, and we would have an n squared algorithm. But this one, where we have a single for loop, is order n. Now, imagine for a moment that we know a little bit more about our list. Say we know, for instance, that our list is sorted. We could use that information to more efficiently find the element in our list. For instance, we could first look at the element in the middle of the list. If that element is bigger than the one we're looking for, since the list is sorted, we know that the element we're looking for must be in the first half of the list. And then we could repeat that process, looking at the middle element in the first half of the list. And again, if that element in the middle of the first half of the list was bigger than the one we're looking for, then we know the value we're searching for must be in the first quarter of the list. And this way, we could arrive more quickly at the element we're looking for because we're breaking down the list by halves with each step. So if we know we're dealing with a sorted list, we can say, for instance, this isn't even, sorry, I'm ahead of myself. I'm talking about this one. Sorry, let's back up just a moment. If I'm working with a sorted list, the first thing I might think of doing is, well, I don't have to, if I'm iterating over the list looking for a particular value, I don't need to go all the way to the end. I can just go through the list, and once I encounter a value in the list that's bigger than the value I'm looking for, then I know that I have failed to find the value I'm looking for. Because since the list is sorted, the value I'm looking for couldn't be beyond this element. In other words, if I have a list that's like 1, 3, 8, 10, 21, if I'm looking for the element 9, I would look here, and then here, and then here, and then once I see this 10, I know 9 is smaller than 10, so it's definitely not in the list, because the numbers are only, if I know they're in sorted order, I know that 9 couldn't possibly be in the rest of the list. And this will be slightly more efficient than our previous approach. We don't have to necessarily go all the way to the end of the list before we say that we haven't found the thing we're looking for. So let's time how long it takes to run this method, this algorithm, and compare it to the previous one. So we've made an upgrade to make our approach more efficient by saying, since we know the list is going to be sorted, we can stop early. We don't have to go all the way to the end of the list before we conclude that we have not found the element we're looking for. And we can find this find element sorted solution is slightly faster. It takes less time than find element. But again, it appears to be roughly linear in relationship. This is a little bit faster for some reason. But again, depending on the exact details of what lists get generated here, we'll see some noise in the exact times that we measure. They may be higher or lower by some amount. So we again see something that looks like a roughly linear relationship. So this is still an order n algorithm. It's somewhat faster than our original approach, but it takes roughly the same amount of time. But using the approach that I described earlier, we could do even better still. The approach I mentioned earlier, to remind you, is if we're looking at this list and we're looking for the element 9, we'd look at the middle one and we would say, okay, is 9 bigger or smaller than this element? And since it's bigger, we would then look at this half of the list. And then we would compare it maybe to 10, and we'd say, is it bigger or smaller than 10? And since it's smaller, we'd be looking for a number between 8 and 10. There is no such number, so we quit. But now we only had to look at 2 elements. And we kind of broke the list down into parts. Halves, then quarters, and then we would have done eighths. And by breaking the list into parts, first the left half and the right half, and then, if we discover it's to the left of 21, we would have the first quarter and the second quarter, and then the first eighth and the second eighth, or something like that, or the third eighth and the fourth eighth. We essentially locate our object, our value of interest much, much quicker. So here's an implementation of that algorithm I described. If, first of all, there's nothing in the list, then we just return false. If length of the list is less than 1, meaning if it's empty, then our element's not in there. Then we calculate where the midpoint of the list is. If the element is the midpoint, then we're done. Otherwise, we check if it's larger than our the element we're searching for. If so, then we look for our element by calling this function itself. This is recursion in the first half of the list. So you might want to look back at the Pi program flow notebook for the section on recursion if you want more help understanding this function. But basically, the idea is now we try and do the same kind of search, but only on the first half of the list, since the element in the middle is bigger than what we're looking for. And if the middle point is less than what we're looking for, then we'll try and find our value in the second half of the list, from the midpoint onward until the end of the list. So let's now time how long this binary search algorithm takes, and again compare it to our previous algorithm that was order n, or linear complexity. So we can see this binary search method is quite a lot faster than the previous method. It still looks roughly linear, but in fact it is not, or should not be. A analysis of how the time complexity of this algorithm would show it to be log n. How do I know it's log n? Well, in each step, I'm splitting the list in half. So I'll take, essentially, in order for me to take one additional step in my algorithm, in my solution, the length of the list has to double, because each step reduces the size of the list by a factor of 1/2. I keep halving the list over and over again until I find the particular thing I want. And that kind of having to double the input for one additional step means that for each additional step, I have to do essentially have an input growth of 2 to the n, which is exponential. Analyzed in the opposite direction, we would say the number of steps is log base 2 of n, or just log n. So the amount of steps that I'm doing grows logarithmically in the size of the input. And just to give you an idea, if you're not familiar with logarithms, to give you an idea of what they look like, or how slowly they grow compared to a straight line. I mistyped something here. There we go. The logarithm grows so slowly that we can hardly even see the difference over as n becomes really large. The logarithm grows hardly at all. If we reduce this a little bit down to say 100. We can see the logarithm does grow a little bit away from 0, reducing it even more, down to 10, so that these two are even closer together. we see that still, even here, the logarithm grows much more slowly than a straight line. So logarithmic complexity is much, much better than linear complexity. Logarithmic algorithms will be much more efficient. But it's not always possible to find a solution to a problem that runs in logarithmic time or constant time. Sometimes linear time is the best that you can do. And in fact, our ability to use this binary search approach was only possible because we took advantage of knowledge that the list is sorted. It's only possible to use this binary search method when the list is sorted. If the list is not sorted, we could not do this. We would first have to sort the list. And sorting, generally, takes, on average, n log n time. So, if we had an unsorted list, then in order to use the binary search method, we would first need to sort the list, which takes n log n time, and then search, which is log n time. So on the whole, the time complexity would be n log n. However, if we were going to be searching the same data structure over and over again, it might be a good idea to pay this n log n price just once, and then we only pay log n time each time we want to search afterwards. Because once it's sorted, we don't need to sort it again. So, in this lecture, we extended our analysis of the computational complexity of algorithms by considering a somewhat more complex example or complicated example. We found that the time complexity of a solution, or what time complexity we can achieve, often depends on the particular details of the problem we're trying to solve. For instance, here, if the list was sorted in the first place, we could find a faster solution, one that had lower time complexity, log n instead of n. And we found also that if we're solving some particular problem, we might need to consider contributions from different steps in that problem when deciding what to do. If we are presented with an unsorted list and we are only doing search once, we might not want to pay the n log n time to first perform the sorting before doing a binary search. But if we were going to be searching many more times than n, the elements in the list, then it's not a big deal to sort it once and then search it many times. As usual, I did not read to you what's written in the notebook because you're capable of reading yourself. I just simply kind of narrated as I stepped through the code and explained the ideas. But I do recommend that you come through the notebook and read and follow along yourself independently as a supplement to my description. In the next video, we'll be talking about other techniques for improving time complexity and the trade-off between time complexity and space complexity, or the amount of memory we expend on a particular problem. We'll see that we often trade between these two things.